Welcome to another GCBASIC demonstration. This is for the PIC18FxxQ24 series. So what we're looking at here is part 16, program, SAF memory, EEPROM, data blocks. It's all about using the resources within the microcontroller, what I call the storage. So please like and subscribe the video, let it run all the way through. Because those metrics are extremely important to YouTube and me. So, storage within the chip. That's program memory, SAF memory, EEPROM data blocks. Let's get into it. Okay, I'm assuming that you've installed your GCBASIC software, your programmer. You've got a Q24. You've got some LEDs that operate, a pot, switches. Most importantly today, USB TTL converter. So let me look at this cam here. This is mine, Q24 attached here, PICKit GUI attached through here. It's just one of these from PIC Circuit. We sell our own, but I use this one. Plug that back in. I've got 4 LEDs here attached through these flying leads, a potentiometer. But really, the only thing I'm going to be using today is the USB TTL converter. That's the only thing I'll be using today. I'm just going to make sure that's connected because I'll be using that. So I've got that all connected up. Great. We won't be seeing that much today because we're going to be looking at the terminal. So this is the most important USB TTL. Okay, because I'm using a particular power domain called VDDIO2, I must put power to VDDIO2. I'll explain. So I've got my typical voltage in historically to VDD. I've got 5 volts attached to there. I've also got 5 volts attached to VDDIO2 because I have got my serial out coming in here. So if I can draw a little picture, this green area here is a power domain of its own, and as you can see, it's got, you must put power on that power domain to make it work. Fail to do that on C6, C5, C4, C3 respectively, and you will get you'll get output, but it will be too low a voltage. Okay, and it won't work. Great. So what am I doing? As I've said, I've got VDDIO2 with power, and I'm using C.6 as my transmit. My transmit is for the USART. So what are we going to be looking at? So we're going to be looking at storage. Let me just give you a quick overview. There are many different types of storage inside of a microcontroller. There's program memory, that's number one, and that contains your programs. An area called storage area flash, or SAF. I have, like, for instance, on the Q24 datasheet and all the data sheets I've searched, and it's hard to find the details of SAF, but essentially I'll give you some great insights into that. And that sits, if you look at the diagram on this Q24, in this red box at the top right hand corner here. Okay, and you've got program memory and an area called SAF, and you can control that SAF, and we're going to do that. You've obviously got data RAM. You've got data RAM at 2, but that's volatile. So that means you turn the chip off, you lose your data RAM, but it does exist. And we can create variables in there, and we've been creating different types of variables throughout these set of videos. And then the third area is data EEPROM, which is this lower block here. And that consists of 512 bytes for this particular chip. And I always consider that as a peripheral because it's not part of the core, but that's just my view. So, program memory. You put your program in there, you can put some reference data, you can put pictures in there, and we have a thing called PFM for direct addressing. So you can write direct into, you can read and write into the program flash memory, not with a programmer, but within your code. So that's quite useful. So you can put bytes of data inside of the program memory, and there's 32 kilowords in here. So I could write a little bit here, some reference data to a particular location anywhere in memory. Accidentally, I could also do it in the middle of the program memory. So it has a bit of a risk, but don't be doing that. Now, why have I got 2 diagrams? Because sometimes, like with GCBASIC, The program starts at address 0 and goes that way. It goes upwards. Even though I'm drawing a downwards arrow, it's actually 0, 0 to the end of program memory. Other compilers might give you a little jump statement at 0, and it says jump to this location here. And this diagram is sort of important because depending on what type of compiler you're using, whether it's a bottom loader or top loader, if you write something here into program memory, it would work. But when you're using a top loading compiler, it would obviously destroy your program. So just be careful and be conscious of the type of compiler. We're a bottom loader. GCBASIC is a bottom loader. It always starts at 0 and works its way up. And we're going to see an example of doing that. Now, that means that you could write reference data, lots of reference data, behind at the top of memory here. You can write it at the top of memory, or you can write it after your bootloader. Just be careful, not your bootloader, your jump vector into it. So that's the jump vector. You can put reference data anywhere. So you can do that, and I'll show you how you can different techniques to make that work really quickly, and to ensure you don't mess up your program, the blue stuff. SAF. SAF is, as it says in that box at the bottom, is designed for storing non-volatile data that can be protected to ensure data integrity and security. Now, that's similar to what I'm going to show you called EEPROM, but it sits inside of program memory, and it's always at the same location. It's always from the top of memory downwards, and it comes in little pages of memory, and you can control those in your configuration. And if you're using a bottom-loaded program compiler like GCBASIC, it doesn't really matter about SAF. You just need to retain it. But if you're using a top loader, you must offset your program to not overwrite the SAF data when you program the chip. So you mustn't overwrite that with your program data. So it program fills up the memory or the program memory. Don't overwrite your SAF data at the bottom. This is like an interface here, and I'll show you a picture of that. So what we can do is we can also use EEPROM. And EEPROM is a block, or is a block of data, 512 bytes in this particular case, for this particular chip. And you can put reference data in there as well. Different set of commands, different set of instructions, but it's there, 512 bytes, quite a lot. But also what we've got in GCBASIC, we think called data blocks. So you've got a data block, which you can just put inside of your program memory, and it's automatically managed. So you don't risk overwriting your program. And we'll show you that as well. And both of these areas, EEPROM, all these data blocks, can be used for reference data. Quite a lot of reference data, that's why it's been implemented. So what we've got is a little bit of complexity in terms of options here. But because we can write into program memory, SAF, which isn't even shown on this diagram, you see, or you can write into data EEPROM. Lots of different areas, and they're all forms of storage. So what we're going to do is we're going to walk some examples of walking through managing the program memory, managing the SAF, and the EEPROM and data blocks. In GCBASIC, it's all pretty simple. Okay, let's see what we've got running here. I've got terminal. I'll clear that down. I have to fiddle with that in a bit. And I've got some demos. Okay, well, let me just shut everything down. Control B, Control J. Back to the old logo. Right. Control B. Open up demonstration 260, showing program data to the serial terminal. Control B to shut that down. Let me zoom in on that for you. So this is a standard header. I've got my chip specification. I've got my PPS init PPS set up so that I've got my USART set up. The rest of this header is exactly the same as we've seen in all the other demonstrations. Here's the main program. So what we're going to do, the first thing we're going to do is we're going to read, PFM read, from an address. We're going to put that address, the returned value will come back in a variable data word. So this is the instruction, PFM read, and we're going to read from the program memory. And we're just going to put it on the screen. And the addresses we're going to read are from 00 to 001F. That's the first 32 bytes. So we're actually going to read from 0 to 32 and put it on the terminal. And then what I'm going to do is I'm going to write some data, and I'm going to put it in, it's almost like randomly, 3F F8 and 3F FC. And we're going to put two values in there, a byte value and a word value. And then we're going to read that back and put it on the screen. But we're also going to see this evidenced in a programming tool. So I write it out here, I write it out there, and I'm going to read it back in a little loop. And then put it on the terminal, and then just loop the chip forever. Function key F5 to program the chip. Let me bring the terminal in. Where's the terminal? Well, here's the terminal here. Hang that off the side of the screen for you. There you go. Why hasn't that worked? Let me just rescan things, connect that up. Power cycle my chip. Oh, there we go. Great. So what I've got is it says here, I've got at address 000 through to 1E, which is 30, by the way, 31. I've got these addresses sitting in that memory space. Well, let me prove it to you. I'm going to start up my favorite programmer, PICKit Plus. We're going to read the chip. Read the chip. And we're going to see the same results, hopefully. And we're going to see the same results. It should start with EF06. Oh, need to scroll again. EF06 followed by 00. That is the jump vector. FFF. Look at the end of, look at number 8, look, DA06, like, or here. And the final one is 87. 87. 4C in hexadecimal. So we can read the memory, which is great. That means that we can read program memory, which proves to us we can put reference data in there. Now, I wrote two of the values. I wrote them at address 3F F8 and 3F FC. Well, why don't I just cursor through? Oh yeah, I've got a cursor through. What could be easier? Oh, there it goes. Look. 3F. There it is at the top of that line. But just zoom in a bit closer for you. Here it is. 3F. That's the byte I wrote out, and that's the word I wrote out. 55AA. If I look at the source, I wrote out exactly that address. So we have commands that allow you to put stuff into memory. The danger here is if you get the address wrong, you could overwrite your program, but you can do it. Don't care. It's an available capability. Control B. I'm going to open up 270. As I said earlier on, SAF memory sits at the top of memory, but it comes in pages and it's managed in pages. Those pages can be controlled in your configuration. So if you go into PICinfo, you can control if you write and read these things. But this program can write a whole page, a particular byte within SAF, because it is a particularly difficult area to manage. Now the header in this particular program is identical to the previous, has the serial only. And what I'm going to do is I'm going to write you can study the program on your own. I've created a little array called my buffer, and I'm going to put 8 values into my little array called my buffer. And then all I'm going to do in here is I'm going to write that out to the SAF memory. So how do I do that? Well, essentially you say SAF write block. And because I've explained they come in blocks of 128 bytes, I've said put it at 0. Therefore, you don't need to know where it lives in memory. It will just put it at the first page of SAF. You've got pages 1 through to the end, and at the top of this program it explains that in some detail about all the different block addresses and pages, etc. But essentially it starts at 0, and if you wanted to know how many blocks there were, you'd go you can use a constant. Look at my program. So I'm going to write out my buffer and the number of bytes. Then I'm going to read it back just because I can read it back and put it on, and I put it on the screen. Okay, let's watch that. So create a buffer, write it out with the SAF write block, read it back. What could be easier? Clear that screen. Great. Now, this is the total program. So I wrote out some values. I wrote out 8 bytes. Let me just check what my bytes were. They are 202C. So somewhere in memory, I will find a block of memory in SAF, which is in the program memory, but at page 0. Let's find it. Let's read the chip. Now, in the bottom of this programming software called PICKit Plus, you can actually control your SAF data, but it's going to be color coded and we can see it quite nicely. So here we go. So we are looking for 2C20. If I just pull down on here, it's color coded. So I can see the block. Oh, and have I got it all selected? No, I haven't. Look, let me just select all the SAF. 2C20. 2C20. Now, because this is in SAF memory, you can protect that with the configuration now, and it will never get overwritten. You can also do things like this. You can inside of your software, you should be able to erase the chip, for instance, and the programming software should maintain your SAF memory. So it's going to erase the chip and then put back the SAF. It's restored it, look. So look, the chip is actually empty, but the SAF has been restored because the programming software has maintained that for you. But you can also do the same from config. And so the ability to write out into SAF is quite important because this is a very big art. This is 1,024 words, I believe. That's right. So we just wrote out a little buffer. Next time, what we're going to do is we're actually going to write out a relative address. So I'm just going to write out some words, some bytes into the relative address, and because that's a relative address, you just start at 0 right the way through to the end. Program that. So I'm just going to write out 7 bytes. And what am I writing out? I'm writing out that address with this data byte. What is that data byte? Oh, I'm reading it back in. I'm so sorry. Then eventually what I'm going to do is I'm going to write out some random words. They look like random words anyway. And I'm going to put them in particular locations. And I'm going to put them in addresses 8, 10, 12, and 14 decimal. So you can write out whole pages like a buffer, like an array, or you can write out specific words into SAF memory using these commands: SAF write word, SAF write a read word, etc. And so what we get inside of our terminal is 2 blocks. We got the first block we saw before, which is from the array, and this is from the actual, but this is writing out words at a time. And we're just writing them out into the locations 8, 10, 12, and 14. And we saw that in actual fact if we look very carefully at the PICKit software. we can actually see the second row of information here, which would be BAF 01F D271, etc. So you can write very easily into program memory using PFM write and read and SAF write and read. They're commands. They just manage that environment. Now, what else you can do, and there's a dump program in there. You're actually seeing a dump program, which I'm not going to go into. Control P, open up 280. But as I said earlier on, there's a complexity when you're trying to write things to program memory. You don't want to overwrite what was there in the past. So in GCBASIC, same header, we can actually create what's called a data block. And those data blocks can be in EEPROM or they can be in program memory. And so to use this, you just literally say EEPROM, give it a label, a unique label, and then you have an optional address, which I'll talk about, and then you just put your data in there. You just type your data in, and it can be strings, it could be text, just put stuff in, hello world. This goes into EEPROM, so you just say EEPROM, end EEPROM, EEPROM, end EEPROM. There's a set of data here, but it's actually going to put it at location 16. And so previously, in previous videos, I showed you how to do read table. This just puts it straight into EEPROM. When you program it, it will arrive in there. There's no need to do read tables. Puts it in. And this is the same for data and end data. So this will attach a block of data called my data block 2 at the end of your program memory, and it will be safe, meaning that you will not risk overwriting. And this gets used extensively within microcontrollers that I've seen, and I've seen major use of this in the last year for a whole operating system that's been loaded into the program memory, and it's just put at the end of your program, so you don't have to worry about overwriting it, writing bytes out. You just put your data in here. And so I've got two blocks. I've got one called my data block 2, series of numbers, and my data block 1, which is a series of hexadecimal words. Now look, this has got an adapt. This says by byte, and this says there's no modifier here, therefore that will be a word. So let's program that. What we're going to do, we're going to look at the assembly file as well. Bit of interest there. So this is where I'm going to read in the EEPROM. Let me just uncheck that. Read it in. And here we have some values. 0, 1, 2, 3, 4, 5. Well, is that what we actually asked it to put in? Exactly what I asked it to put in. And then at address 16, I asked it to put in 54321, and there is 54321. Something put it directly there. Just press Shift F7, or you can use function key F4, open asm. If you look at the bottom of here, it's got a data table. It says it's a data table for a Q24 at address 3800, and it lays out your data for you automatically. So you can easily create data within EEPROM, which is automatically uploaded when you program. And it does the same for AVRs. Whilst we're here, we can also see this data block. This data block, 8 items, it puts them at the end of the program. My data block 1 was a series of words, and you can see these represented here in this into the assembler, and it says end of data block. So let's read that into PICKit Plus as proof. So what we're going to do is find the end of the memory, and then we should see a sequence of bytes called 1, 2, 3, 4, 5, and we should see a sequence after that of 1, 2, 3, 4, 5, 6, 7, 8 in hexadecimal. So let's find the end of memory. And here it is, look, 1, 2, 3, 4, 5, 6, 7, 8 in bytes. And now in words, 1, 2, 3, 4, 5, 6, 7, 8, 1, 1, 2, 2. And it's exactly what we've programmed it in the data blocks. That's clever. So how do you use that? You use that very easily. If I show you on a terminal, I must have programmed it now. It says here, program read. It could be PFM read, it's the same command in reality. PFM read, my data block 1. Oh, we got what's this funny @ sign in front of it? Well, that funny @ sign in front of it will return the address of that label. So I've said program read, the address of that label plus an offset. What's the offset? 0 to 0. See a little loop lot, for next loop, offset. That'd be 2, 4, and 6, and go and get the value of that from the program address and put it in a variable called myDataWord, put it on the screen. And that's exactly what we get here. Look. 1, 2, 3, 4, 5, 6, 7, 8, 1, 1, 2, 2, 2, 2, 2, 2. But we put it in memory. So we can manage the memory with some ease. We can do program writes, program reads, SAF writes, SAF reads, EEPROM writes, EEPROM reads, and data blocks into EEPROM and into the program memory. And you could fill the whole memory with data blocks. It doesn't matter. You just got to watch you don't overfill it. And literally, you'll get a warning anyway. But this is very simple as putting in commands, EEPROM, and data and ending them. If you look in the help, press function key F1. Let me just type in data block. There'll be one called data. Let me just put data in there. Sorry. Data in capitals there. And here's an example that was actually used. So this guy put in Fabrice Engel, he actually put in some data variables. Let me just pull that up so you can see it. He put in some strings and then put that into his EEPROM. Oh no, that's a data block. Look, data block, version data, and then he can read that version data back in as he wishes. And he can put it out on the screen. It's a lot easier than strings, by the way. Okay, good. Let's get back to PowerPoint. So we've seen program memory, SAF, EEPROM, and data blocks. All right, next time out we'll be using CLC, which is pretty exciting. Enjoy.